Hello everybody. In this video we will be discussing about buffer solutions. So to start with this, a buffer solution means something that, say for example, you take pure water and you add an acid or a base to it. If you add an acid to it, the concentration of H plus ions in the solution will increase and that will change the pH. That will in fact bring down the pH of the solution. The pH will become lower because it is an acidic solution, and if you are adding a base to any solution, it will increase the concentration of OH minus ions and that will increase the pH value because the solution will become basic. A buffer solution means if you are adding a small amount of acid or a small amount of base to that solution, the pH of that solution will not change. So that is what a buffer is. A buffer solution's pH or a buffer solution is a solution whose pH does not change when you are adding a small amount of acid or a small amount of base to it. Now buffer can be of two types. One is an acidic buffer and the other one is a basic buffer. If you want to make an acidic buffer, you need to take a weak acid. Let's say that I have a weak acid something like HA. As an example, you can have CH3COOH. In a similar way, if you want to make a basic buffer, you should have a weak base something like NH4OH, and let's call a weak base in general as BOH. So example of it is NH4OH. Now along with the weak acid or the weak base, say for example I talk of an acidic buffer, the weak acid, along with it you should have a salt of weak acid with strong base. Listen to it very carefully. So along with the weak acid, if you want to make an acidic buffer, you should have a salt of weak acid with a strong base. A strong base, an example is NaOH. So salt of this with NaOH will be CH3 COO minus Na plus. So these two things together can form a buffer solution. In general, if HA was an acid, I can take a salt with strong base Ba. So you can say that BOH was a strong base and salt of HA and BOH was Ba, and that is the salt of that weak acid with a strong base. Similarly, if you talk of a basic buffer, can you think and tell me what do you require here? It was a weak base. So we need salt of weak base with a strong acid. So if I talk of a strong acid is, example would be HCl. So NH4OH plus HCl, the salt would be NH4Cl. So NH4OH and NH4Cl together will form a buffer and you will call it a basic buffer. In general, I can say that if BOH is my weak base, then salt with a strong acid will be Ba. It's just in a similar way, if BOH was a weak base, I am taking a strong acid, let's say HA is a strong acid, and salt of BOH and HA will be Ba. So BOH and Ba together are going to form a basic buffer. All in all, how have you formed a buffer? That is what you need to learn from here. Buffers can be of two types. One is an acidic buffer, the other is a basic buffer. For an acidic buffer, you need a weak acid with its salt with a strong base, and for a basic buffer you need a weak base and its salt with a strong acid. Now you need to understand the equations in this. So I'll do one thing, I'll derive the entire equations for a basic buffer, and for an acidic buffer you can derive the things by yourself in a similar way. So let's go ahead first with a basic buffer. If I take a basic buffer, I said first of all what I need is a weak base, and a weak base is NH4OH. So NH4OH will dissociate, and the way NH4OH dissociates will be NH4 plus OH minus. Now when I say NH4OH, the solution is in water, okay? So there is NH4OH plus water giving you NH4 plus OH minus, but just to maintain that the balance, just to give you a balanced equation, I have written it like this. So NH4OH dissociates in the following way. Now in this solution itself, I am putting a salt of NH4OH with a strong acid, that is I am putting NH4Cl. Now because NH4Cl is a salt and every salt is a strong electrolyte, NH4Cl will completely dissociate, giving you NH4 plus Cl minus. Now I have drawn a single arrow over here because NH4Cl was a strong electrolyte. A double arrow has been made because this was a weak electrolyte, and the reaction, that is why, was reversible. Here it will not be reversible. No matter how much ever salt you take, it is going to dissociate completely into the corresponding ions. Now this is where the equations come in. I need you to write the dissociation constant for the weak base. The dissociation constant for weak base was Kb, and Kb will be written as NH4 plus into Cl minus the whole upon NH4OH. Sorry, NH4 plus into OH minus into NH4OH. Now think a little over this equation, okay? See, initially what we will do is we will not take the salt. Initially we will take only the base. So if you are taking the base and you are putting it in water, NH4OH is already a weak base, and that weak base will dissociate very little. Say for example, we have taken 10 moles of NH4OH, and out of 10 moles of NH4OH, 0.1 moles are going to dissociate. Only 0.1 moles dissociate because this is a weak base. If 0.1 moles dissociate, we will be left with 9.9 moles of NH4OH, and we will have 0.1 moles of NH4 plus and 0.1 moles of OH minus. Assume that everything is happening in a solution of 1 liter, so the concentration will be number of moles divided by 1. So whatever are the number of moles, they are the same values for concentration also. So if you put in those values over here, the Kb value for NH4OH will turn out to be 9.9, sorry, 0.1 into 0.1 upon 9.9. It's 10 power minus 2 upon 9.9, and let's take 10 power minus, 9.9 approximately as 10. So we have 0.1 into 0.1 upon 10, that is 10 power minus 3 as the value of Kb for NH4OH. So keep in mind this value, which is 10 power minus 3. In reality, it's not 10 power minus 3, it's I guess much smaller than this. But for now, let's just take, just to understand the concept, I am taking some numbers at random. So the Kb value we have is 10 power minus 3. In this solution, we are putting 10 moles of NH4Cl extra. So when 10 moles of NH4Cl have been put, now NH4 plus will be 10 moles and Cl minus will also be 10 moles, because the entire NH4Cl will dissociate. Now how will this in the same solution affect the equation over here? The Kb is, the Kb expression is written as NH4 plus into OH minus upon NH4OH. NH4 plus is now present because of this as well as this equation, and in the equilibrium equations I have said that whatever concentrations you put are the concentration of the species in the entire solution. So in the entire solution, NH4 plus was already 0.1 present, you are putting 10 moles extra. So now NH4 plus is going to become 10.1, so this becomes 10.1, but after this becomes 10.1, OH minus was 0.1 and NH4OH was 9.9, roughly equal to 10. Let's write it as 9.9 for now. But now if you calculate these numbers, the evaluation will not be 10 power minus 3. The reaction will not allow you to do that, because Kb value for any given reaction remains constant except when you change the temperature, and currently you have not changed the temperature. So the reaction will not allow you to change the Kb value. So Kb value currently has got increased. Reaction will try to bring it down to 10 power minus 3. And how will it try to bring down this value? To bring down this value, either NH4 plus and OH minus have to reduce, or NH4OH should get formed, and that will happen if the equilibrium shifts in the backward direction. Now imagine this, already this was a weak base and the equilibrium was mostly on the left hand side. You are bringing it more on the left hand side by adding the salt here. The salt had an ion common to the ion over here, and because of that common ion effect, the dissociation of this weak electrolyte, which was already less, got suppressed even further. Now how much it will get suppressed can be calculated. We are not going to calculate it, but yet I will show you the procedure by which you can calculate it. So say for example, NH4 plus and OH minus, X moles of NH4 plus and OH minus get combined. So I will have 10.1 minus X moles of NH4 plus at equilibrium, and for OH minus it will be 0.1 minus X, and 9.9 were already present of NH4OH. Now more amount of NH4OH will get formed because X moles of NH4 plus and OH minus got combined, X moles of NH4OH got formed. So in the denominator it will be 9.9 plus X. And finally this was the expression for Kb, the value of which was constant at 10 power minus 3. You can solve that equation, it will be a long process I know, but that equation is made. You can solve it to get the X value, and that is why after you get X, you will get the concentration of all the species in your solution. You don't have to calculate it. This is merely for your understanding purpose. Now from the numbers that we have just seen, we need to make some inferences. Have a look at this number, 10.1 minus X. This is the concentration of NH4 plus at equilibrium. Just try to recollect what was that X. X was the number of moles of NH4 plus and OH minus that got recombined, giving you NH4OH. So initially you had 0.1 moles of NH4 plus. Some number of moles out of 0.1 got recombined. So that number of moles which got recombined were X. Now X, that is why will be a number lesser than 0.1, because out of 0.1 some number of moles got recombined. So that will definitely be less than 0.1. So X is less than 0.1. And 10.1 minus a number less than 0.1 will be approximately equal to 10 only. The inference is this number is approximately 10, and that is the NH4 plus concentration. But that 10 came because of this. So my point over here is, see, NH4OH was a weak base, so it dissociated very little. So whatever NH4 plus was present because of the base was very little. Most of the NH4 plus in the solution is present only and only because of the salt. So we will say that the NH4 plus ion concentration is approximately equal to the salt concentration only. And for all practical or all calculation purposes, we say that the NH4 plus ion concentration will be taken as the salt concentration only. So this NH4 plus ion concentration is equal to the salt concentration, and similarly try to think over it, what is the NH4OH concentration at equilibrium? Now NH4OH concentration at equilibrium is 9.9 plus X. We just saw that X is a number which is slightly lesser than 0.1. So that 9.9 plus X will be approximately 10 only. Now that NH4OH concentration is approximately 10 because you had taken 10 moles of NH4OH. There is another way of explaining this. See, NH4OH had to dissociate very little because it is a weak base, and by adding NH4Cl you have suppressed the dissociation even further. So NH4OH, whatever you had taken initially, only a little amount of it has dissociated at equilibrium. So at equilibrium, whatever NH4OH concentration you have is approximately equal to the NH4OH that you had taken at the beginning, and that is why we say that NH4OH concentration at equilibrium is approximately equal to the NH4OH concentration which you had taken originally. So we say that NH4OH is the concentration of base that you had taken for making the buffer solution. So these are two things that you need to infer from the numbers. I will get back to these two things a little while later when I start deriving the equation for a buffer solution. Now the first thing you need to know over here before you move on to that equation is how the buffer solution will work. I had mentioned that a buffer solution means something to which if you add an acid or if you add a base, the pH value will not change. So pH value will not change means the H plus ions or the OH minus ions that you have added extra have to get consumed. So let's go for the easier part first. If you are adding H plus, that is an acid, to this solution, what will consume that H plus? The answer is easy. In the solution, these are the species you have. You don't have NH4Cl because it has dissociated completely. These are the species you have. So if you are adding H plus will be neutralized by the OH minus that you have in the solution. Let us say I have added 0.1 moles of H plus. So 0.1 moles of H plus are going to consume those 0.1 moles of OH minus and get neutralized. But if 0.1 moles of OH minus are consumed, then that affects the pH of the solution. But hang on, it's not yet over. It is the Leach-Italius principle which now tells you that because you are consuming OH minus, the products are decreasing, and because the products are decreasing, the reaction will try to increase the products and equilibrium will shift on the right. So more amount of OH minus will get formed, and whatever OH minus was consumed by H plus will now be regenerated. So the H plus that you put in has been consumed, and the OH minus which was consumed by H plus is regenerated, and that is why the pH of the buffer did not change. Now this is where you might be thinking that I have played a little trick over here. The answer is yes. I did not give you the insights, I did not explain that concept with the help of numbers. So let's try to analyze it with the help of numbers, and you will realize whether the entire OH minus that got consumed is actually getting regenerated or no. So we need this expression again, Kb. 10 power minus 3 is NH4 plus into OH minus divided by NH4OH. We had 0.1 moles of NH4 plus. Okay, I know that after adding NH4Cl the numbers are going to change, but let's just say for example now the numbers are these. So just deal with these numbers. These numbers will be sufficient to explain the concept. Okay, as per this the numbers will not be the ones I am using here, but let's just stick with the numbers here for now. Like I said, it's enough to explain the concept which I am teaching. So there are 0.1 moles of NH4 plus, there are 0.1 moles of OH minus, and there are 9.9 moles of NH4OH. Like I said, you added 0.1 moles of H plus, they made this concentration 0. So now the reaction tells you that you cannot have the numbers like this. The numbers have to rearrange themselves so that you get a 10 power minus 3 back again as the multiplication of these numbers. So the reaction tries to ensure it by producing NH4 plus and OH minus. But now when OH minus is going to get formed, see, when OH minus gets formed, NH4 plus will also get formed. So NH4 plus, which was originally 0.1, will now start increasing and it will become something greater than 0.1. See, initially it was 0.1 into 0.1 giving you 10 power minus 3. Okay, 0.1 into 0.1 upon this was roughly 10, giving you 10 power minus 3. But now because this is already 0.1 and now because of NH4 plus getting generated, it will not be 0.1 into 0.1. This number will be much bigger than 0.1. And this number cannot approach 0.1 now, because if this becomes 0.1, the product will be bigger. So this number should be a little smaller than 0.1. And because this number is smaller than 0.1, this might be something like 0.099. So the entire OH minus that got consumed is not getting regenerated. It is getting regenerated in a little lesser amount. That will affect the pH theoretically, but the change in pH, the quantity by which the pH is affected, is very little. So that is what a buffer solution means. See, OH minus concentration remains approximately the same, not exactly the same. And that is why, because this was approximately the same, we say that the change in pH of a buffer is negligible. And because it is negligible, we say that the pH is constant. And that is why I had mentioned at the start that the pH of a buffer does not change when only a slight amount of acid is added. If you add a higher amount of acid, then the change you get here will be significant. And that is why you will see significant changes in the pH of a buffer when you add higher amount of acid. So this is the entire logic behind the buffer solution. In general, if you want to view it in a very short manner, you can say that whatever H plus you added got consumed by OH minus, and whatever OH minus got consumed got regenerated again. But check the numbers. Like I said, full OH will not get regenerated. A little part, a little difference will remain in the quantity of OH which was originally present and present after the addition of acid. So the change in pH will be there, but negligible change. Okay, so that is about the concept of pH, and that is about buffer action. Just to say that again, if you are adding acid, it is OH minus of a basic buffer which will neutralize the acid. But what if you add OH minus? If you add OH minus, then it is very simple. You add OH minus, already NH4 plus is present in excess, and because you are adding OH minus, the Kb value goes up. It will come down by combining NH4 plus and OH minus. So whatever OH minus you have added, already NH4 plus is present in excess, NH4 plus and OH minus will combine and they will give you NH4OH. The calculations will again go in a similar way. And again, when you think of it in terms of numbers, you will realize that if you are adding 0.1 moles of OH minus, then 0.1 will not combine with NH4 plus. Only most of them will combine. That is, out of 0.1, 0.0999 will combine. But that 0.0001 will remain extra in the solution. So the pH will get affected only marginally, and that is why we say that the pH almost remains constant even when OH minus is added to the solution. So to say it in just one line, we can say that whatever OH minus is added will combine with NH4 plus and form NH4OH. So whatever OH you added got consumed, and that is why the pH of your buffer remain unaffected. So that is about buffer action. Now I've been talking about pH, right? So there should be a formula by which you can calculate the pH of a buffer, and that formula is what we will be deriving from here only. Just forget the numbers for now and focus on these parts that I had mentioned. NH4 plus is the salt concentration and NH4OH is the concentration of base. Rearranging this, so if you rearrange this, you will have OH minus ion concentration as Kb multiplied by the concentration of base divided by the concentration of salt. Now because you wanted pH, you actually need the concentration of H plus ions. Over here first you will get POH, and after you get POH, go for 14 minus POH, that will give you pH. So just take a minus log to the base 10 on both the sides. Minus log to the base 10 here will make your left hand side POH. So you have POH is equals to, the first term will be minus log to the base 10 of the entire thing, right? But log of A into B upon C can be written as log A plus log B minus log C. So if you talk of log A, it will be minus log of Kb to the base 10. You can call it pKb, and the second term which we are left with, we will keep it like that only. The second term will be minus log to the base 10, the concentration of base upon concentration of salt. And that is the formula for pOH of a buffer solution. If you get pOH, like you had learned earlier, pH plus pOH is pKw, and at 25 degrees Celsius pKw is 14. So pH plus pOH will be 14, and that is why pH will be 14 minus pOH. So that is how after getting pOH you can get the pH of a buffer solution for this case. Okay, so that is about the final equation of a basic buffer. You can derive a similar formula for an acidic buffer also. Let's do it quickly right away. So if you take an acidic buffer, then the equations that you are going to have here . So for an acidic buffer, the equation will be this: CH3COOH. It's a weak acid, so it will dissociate as CH3COO minus plus H plus, and the salt CH3COO minus Na plus will dissociate completely, giving you CH3COO minus plus Na plus. Even in this, with the same explanations, we can say that whatever CH3COO minus is present because of the salt only. So the concentration of this at equilibrium is approximately the salt concentration only, and the concentration of acid at equilibrium is the initial concentration of acid that you had taken in the solution. So this will be the acid concentration, this will be the salt concentration. Go for applying the formula of Ka. The dissociation constant will be CH3 over here. The dissociation constant will be CH3 COO minus into H plus upon CH3 COOH. Like I said, this becomes the salt concentration, this becomes the acid concentration. You can keep H plus on one side, so you will have H plus as Ka multiplied by the acid concentration divided by the salt concentration. Take a minus log to the base 10 on both the sides. The left side will be pH, the right side first term will become pKa minus log to the base 10, it will be acid concentration upon the salt concentration. So that is about buffer solutions. In this video, I have discussed things in a lot of detail, plus the number thing was a little extra, which normally is not done in most of the classes. So I hope whatever I have taught has been clear to you, and you have enjoyed the video. And okay, so that's it with the buffer solution, guys. So thank you for watching, guys, and like I said, I hope whatever I have taught in this video has been someplace helpful to you in your preparations. Thank you for watching.